Okay, so we are recording. Hello,
Yep.
everyone. It's another episode of our podcast, and today our guest is Hon Chong. He runs the company called Cortical Labs, and what they do is actually super unique. It's kind of like out of a sci-fi movie. I don't think you guys have like ever seen anything like this before. Like maybe when you were a kid, you could imagine something like that be possible in the future. And here's the future actually. Here it is, like your chance to, you know, to see it when it's happening. So what Hon does, they try to combine computer and human brain by connecting biological neurons or human brain and chips. And before we start our podcast, Hon, is there any announcement would like to make to our viewers? Because I think at the beginning, when everybody's watching, it's just the right time to make those announcements. Viewers, investors, like anybody. Yeah.
Yeah, look, I think thanks for having me on the show. We're currently in the process of building out the CR1, which I'll talk a little bit more about in the show. But I guess the announcement is stay tuned. Join our Discord, join our Reddit. There's an active community and discussions that are happening. We are building a very complicated stack, a very complex and complicated stack that includes not just hardware, but software and wetware. And we need feedback and help from the community to start thinking about what are the APIs, what are the languages that people want to be using to program these systems, and what are the applications that some people are thinking about, because this is, after all, as you said, very new, very novel platform technology, and we can't do this ourselves. We need everybody on board to contribute to this field. So it's really exciting because it's not every day you get to be at the ground level, building something like this from the ground up.
So yeah, like everybody probably curious right now, what are you guys talking about? Stop this intrigue and just tell us like what it is, right? So yeah, maybe
Yeah.
could you just like introduce, okay, what is it? What are we talking about right now?
So I think we need to take a few steps back and try to understand a bit of history, right? So what we know today as technology is a field that is not really that new if you think about it. We've actually had this technology for the last 70 years, and it all started out when William Shockley created Shockley Laboratories. He brought a whole bunch of really smart people together, and they all kind of didn't like working for him, so they all rebelled, and they were called the Traitorous Eight, and they created companies such as Fairchild Semiconductors, which eventually led to AMD and Intel, and so on and so forth. So this is a really long lineage of what the silicon industry has been, and it's about 70 years old. And so the basic fundamental of our technology today is based on silicon transistors. We've gone from very large vacuum tubes to smaller sort of like transistors that you can buy, like PNP transistors, or NPN transistors from the electronic stores, to really tiny 3 nanometer wafers that have been like photolithographically etched. And it's no surprise, we've had a lot of success, a lot of innovation in this space. But one of the issues we're starting to come across now is the bottleneck that is introduced by what's known as the von Neumann architecture. So all computers that we use today is based on an architecture or a design that's been around for as much as that 70 years, designed by John von Neumann. And to simplify what this von Neumann architecture really is that if you think about this, like when you buy a computer, you have your CPU, and your CPU has a little bit of memory on it, but most of this memory is actually in your RAM. And the issue with von Neumann architectures is the separation between compute and memory results in a lot of energy and heat being generated, shuffling bits back and forth between the memory and the compute and back again. It's kind of part of the whole Turing machine kind of thing. And we're starting to see, that starting to approach its limits, right? I think almost like, what is it? More than a decade ago, we started to see the slowdown in Moore's law, particularly in regard to what's called Dennard scaling. So you had, the payoffs of growing chips that are larger and faster start to diminish because it was just generating so much more heat than what we could deal with. And so the industry started to move towards parallelism, right? You know, if you look at it, the top chip today is 5 GHz. We cracked like, 1 GHz only about 20 years ago. And we've only gone up by a factor of 5 in a sense in the last 20 years or so. And that's because you can't just keep scaling your clock speeds, right? And so we've had to start thinking about parallelism. So, have multi-core machines, what is it, 4, 8, 16, 32 core machines for CPUs. And it's really hard if you think about if you're a programmer and how you actually build systems using that, right? Because a lot of the way we think about when we program systems is in a very linear path, single threaded. You start at a point A, you do point C, point D, and then you find out what the end point is. When you have a multi-core system, you have to do point A, maybe you branch out to point B or point C, and then eventually you all have to synchronize back again. And so multi-thread programming has been hard. Now, one thing that has happened in the last, I guess, 10 years or so, has been the advent of GPUs, so general purpose graphical processing units. And this is, the work that's been paid off by NVIDIA's investment into things like CUDA. And what's really interesting is that this whole multi-processing or multi-threaded programming, the problem goes away if you can do things like linear algebra, because you can take a matrix multiplication and just run it through, and your parallel units are all doing the same computation in a sense, just very large in one go. And really, that was the breakthrough that was really required for artificial intelligence that we know today, particularly the deep learning neural network approach to take off. Because before then, it was pretty much impossible for any machine to crunch through the data required or perform the computations for the abstractions for, say, image recognition and today's LLMs. So anyway, so we've taken a history from all the way from the past all the way to the current present stage. And, our state-of-the-art systems are like GPT-4 O's or whatever they are, GPT-5s, which only work because we have a repository of 30 years or 40 years of human-generated content on the internet that has been fed to these systems in order for them to learn the statistical representations and the connection between words in order to do a very, very powerful autocomplete. And so, this is, if you see what we've actually done, is that we've taken a computer, which is a very deterministic computation system. And what I mean by deterministic computation system is that if I give you, say, the square root of a very large number, the machine will give you a very precise answer very quickly. And so this is what the strength of a computer is, right? You get very fast, very accurate deterministic computations. The problem is that the real world is actually very different in the sense that the real world deals with probability. It's very stochastic. It's very, statistical driven. And so we've compensated for that using our computer systems by building these very large neural networks that try to essentially use a lot of energy and a lot of data to cram in, a compute model that allows us to do the things that we, are pretty amazed by our AI systems. If you look at, say, what the holy grail of, AGI research and what people are trying to do right now is they're trying to build machines that can understand the world and manipulate them, say, kind of robots. Then, these systems may not necessarily be the best approach. And if you think about this, the only true sort of generalized intelligent systems that we know of are biological in origin, right? And so the biological systems, have given us a model of a very fast learning and ability to manipulate the stochastic environments that, you and I inhibit in, and also the fact that they come with very tight energy budgets and constraints in the sense that if you're a bird, right, you're not allowed to spend more energy than you can actually consume, otherwise you die. And so this constraint has actually created a bottleneck and designed for organisms to operate at a very efficient energy sort of consumption rate. So this is, I guess, the two main strengths of these biological systems. And what we've done at Cortical Labs is we've tried to essentially try to figure out how do we take the basic building blocks of, say, the intelligent systems that power these organisms, right? And most of them are sort of either, a distributed network of neurons or a central nervous system like the brain. But what is common to all these systems is that they're made from neurons. And that's not to say that neurons are the only biological compute systems. There are probably, numerous other systems around, but this is the one we know best. And the thinking is that, if we took these neurons, and rather than letting them go through the natural path of, embryonic stage development and turning into a brain, which we know has the ability to do generalized intelligence, compute, consciousness, and so forth. What if we interrupted that process and use the same building blocks to try and build more interesting engineering projects, but harnessing the properties of these systems? Could we build intelligent systems that, exhibit these properties of very low energy requirement and very low data requirements? So that's, the whole gist of why we exist at Cortical Labs kind of thing.
And in general, how did you guys come up to this idea? So like, like kind of your brain is kind of separate entity, and your regular computer is also separate entity. Could you please like explain really more in maybe like simplistic term, how would you even connect both of them? Like
Yeah.
what is it to make them work together? What is there to make them work together, and how exactly it is going to be achieved?
Yep. So if you think about, like, say, the brain computer interface space, right? We kind of know that quite well because, Elon talks a lot about this, connecting a human brain to a computer. And how they accomplish that is by taking a chip and putting it into a brain and then reading the electrical activities out and, passing it and feeding it to a machine, and having the machine interpret the results. You can pretty much do the same thing, but in the opposite direction, which is what we're doing at Cortical Labs. So rather than starting with a whole brain and putting a chip in, right, it's a very complicated process using a whole brain. What we've decided to do was to go the other way and start with the chip, right, which we know exactly how it kind of works. And then we grow simple layers of brain material onto the chip. So that way, rather than trying to say solve for a very high dimensional problem, right? We can start with a very low dimensional problem and understand how that works and build our understanding upwards, right? And this is something, if you think about how we learn mathematics at school, we don't start with a, quadratic or a quartic formula. We start with a linear system first. And understanding how you scale a linear to a quadratic, you can take the same approach, and scale it up to high number polynomial problems. So that's the approach that we do. And the way it works is that neurons communicate between one another using electrical impulses. And because they're on a computer chip, which also runs electrically, we somewhat share a very similar um, communication protocol or language with computers, right? Which is that electrical signals. And so by growing, these neurons on a chip or, putting a chip into a brain, we can pick up the activity of these neurons. So as they're chattering between one another, we can listen to what they say. But we can also, with a little bit of a stimulus into the neurons, provide a signal in. So rather than just listening, we can also whisper back to the neurons. And so this is kind of like this input output thing that I learned about way back in 2018, and I was quite excited about this because it was quite interesting for me when I heard a lot of research labs had equipment that allowed them to grow neurons and, read the electrical activity via a computer and provide a stimulus back. But I was quite surprised why nobody had tried to do compute, right? Because it seems quite the next, step. If you have input output into something that would have turned into a brain, why not try to get it to do some sort of compute for us?
So
So that's kind of how I ended up going down this space and just, trying to pass the information and, make sense of it all.
that's like super interesting. What it reminds me is just, for example, in human brain, you have like few structures. One is more, ancient, like your lizard brain, then amygdala, then your neocortex. So correct me like if I'm wrong or if I do understand it correctly. So basically you grow this brain, and then you have this chip, and then one represent each layer. So this chip would be responsible for more like, exact communication, and then the top layer would be kind of responsible more for like abstract reasoning and and then basically your idea of the startup is to just connect them both and see what type of uh, tasks it can solve in the real world. Is it kind of how
It's
I?
a little bit like that, but I think the key thing is not to anthropomorphize these systems, right? And I think this is what the AI community is a little bit guilty of, which is we try to make our AI systems try to do human things like language and so forth, right? But there's a ton of intelligence that is not language based, or there's a ton of it that is not high level thinking, right? So for instance, um, take a fly, right? A fly only has 1,000 neurons, yet it's able to navigate the world, avoid getting killed, getting swatted. It's pretty hard to kill a fly, find food, reproduce, and do this over and over again for millions of years. So they must be doing something really, successfully, which is, survival and in this real world. Yet we do not have any AI systems that actually perform at the same level as a fly, and a fly consuming whatever the minutiae of energy that it's actually using, right? Because remember, it can only expend the same amount of energy that it can consume. And what is it usually consuming? It's consuming crap. So this is, I think, is really interesting if you take a few steps back and say, well, there are a lot of other problems out there beyond these things. Can we use what we know about these biological systems as the starting point to investigate how it all works? Maybe we're lucky we'll be able to replicate these in silico. Maybe we're not. But I think this is still very early sort of to say.
This is super interesting. So I'm just curious, like, what is the stage of your startup right now? Where are you guys at your research? What were you able to achieve, and what could be the next step in your journey?
Well, the way to think about it is, so we published our work in 2022, but there was a lot of sort of infrastructure time and getting set up that we did before we could get going. And so I mean the company started out in 2018, 2019, and took that long to do. And we noticed that some people also wanted to do this, but they would also have to go through the same process. And so rather than, what's the word? Rather than duplicating efforts, we decided what we are going to do was help the community get going with this stuff by building the CR1 device. So the CR1 device takes everything we've learned from our work to try and encapsulate it into an all-in-one product, right, or all-in-one system, to make it, cheaper, more accessible, easier to program, really as a way of introducing this field to people who may not necessarily have a background in biology or a wet lab in order to grow neurons, right? Or maybe they do have the ability to grow neurons, but have no idea how to program systems. So it's trying to, bring two very disparate fields of engineering and biology together, which usually don't really talk to each other, um, and to simplify that process. So, you don't have to worry about the boring stuff of how you keep these cells alive outside of the human body, because we already figured it out for you, kind of thing.
Mm. And just also, next question, maybe I didn't ask you, probably I should have asked you at the start, but what's your background in general? How did you, in general, are you like engineer or are you a doctor? Could you tell us a little bit more about your past life before the startup?
Yeah, so I'm actually a trained medical doctor. So I did med school, and I worked as a resident for a year or two. But I also am a tinkerer, a hacker, and engineer at heart. So I write software as well. And I had a previous startup. I was CTO of that startup. It was called Clinic Cloud, and we're making connected medical devices. And we were collecting a lot of breath and heart sounds, and this was way back before even AI was a thing. Well, I think it was about 2016, 2017, where, the ConvNet mania started to pick up. And I really wanted to use a machine learning approach to come up with an automatic diagnostic algorithm for these neurons. and sorry, not neurons, for the breath sounds that I had collected, because we wanted to create a way of automating the diagnostic process for asthma. But unfortunately, that startup was a bit too early for its time, and we couldn't really find product market fit. Unfortunately, if I kept it going, if I had reached 2020, I think we would have it would have been a different story because of the whole COVID explosion. But anyway, I was introduced to machine learning. I built, quite a few interesting ML models at that time, and was quite interested in trying to, do this after the closure of my last startup. But the issue was with machine learning, it's the same, I guess, today as well. Back then, you were only as good as the data that you had, right? And nobody had more data than the big tech guys. And so it was only a matter of time before you would be swallowed up and, spat out kind of thing. It's the same thing today, where you're only as good as the amount of compute that you have, and nobody has more compute than the big players. And so, that forced me to think a little bit harder, how do I want to do this? And I went back to the literature, and I read the papers from people like Demis Hassabis from DeepMind, and he said that machine learning AI people, we needed to go back to neuroscience because that's where all the initial discoveries were made. And so I did exactly that. I went spoke to the neuroscientists and say, hey, what's going on in your world? Having been a doctor, I did a bit of neurology, so I could speak some of the language as well. And they told me about, these multi-electrode array devices, and I just was super intrigued by it, because I was like, well, maybe we can use some of the things that we learned from, say, reinforcement learning, or some of these mathematical models of how these, neurons or brains work, apply them to a simple model and see if they actually can do something. So that's kind of my background and genesis of the whole thing.
Interesting. For your startup, like you kind of have a little idea what you're doing already, and what's you think is the top challenge for you right now? And what do you think would be the main next steps in order to get this thing, bigger and going and, kind of get it where it needs to be?
Yeah, the hardest thing at the moment, as I was talking about the history of the whole industry, is that we're very much in the early phases of this space. So what does that mean? It means that while not the same scale, what I have to do right now is not just be an OpenAI. I also have to be the NVIDIA, and I also have to be the TSMC and the ASML. The entire chain and stack does not exist, so we're having to do all of that, which gives us very little time to think about, potential applications, to typical, industries and problems to solve with this technology, because, we've been very focused on how do you build these things? How do you support people building on these platforms? So I guess for us, really the next phase is getting it out there to researchers and getting them to experiment with these systems and, understand what are the strengths, what are the weaknesses, what value does this add to compute? Maybe there's nothing, maybe there is nothing to be earned or learned from this system. In that case, we've done our part for science and we can close the chapter on it. But if there is something else out there, I think it'd be fascinating to know about it.
Yeah, many times, you do the research and you find out something totally different you wouldn't
Yeah.
never expect.
It
Um,
wouldn't be it wouldn't be considered research and development if we already know the answer to it, right? I mean, sorry, it wouldn't be considered research, it would just be considered development. And this is the problem with, the current tech industry or the tech space. We've kind of stopped doing a lot of research and mostly have been just exploiting whatever we've learned. I mean, transformers have been around since 2017, so it's not new technology.
true, true, true. And like, what do you think in general could be a market for this? Like, what kind of product can you build? Like, just, maybe you probably were thinking about like first prototypes, some maybe niche. What would it be?
Well, I think, I reckon things that require um sort of real-time operations with um, tight energy budgets are probably going to be probably where these things are going to excel in. So first thing that comes to mind are probably robots. Robotics, drones are kind of the, I guess, ideal applications for this kind of stuff. Other things are like what can you not test on a computer system that you can with this system, right? And because these are grown from human stem cells, they are human, they're biological, which means that the drugs that we give them also, we give ourselves also affect them. And so this could be a way of, doing personalized medicine or a faster way to come up with a cure for, say, dementia. So there are lots of different applications in this space. And that's why, I think it's particularly very interesting to understand what researchers want to do with this, because they're the ones who have the deep technical expertise and knowledge to use these systems. And also, they're always ahead of the curve, right? That's why, it's called academia, because they're the ability to explore the space and understand before, jumping in and, building a commercial solution for it.
Um, I'm also kind of curious, let's say, for the limitations of this, if you know something about it, would be nice to hear. So, for example, I don't know, how big of this brain can you grow? Like,
Mhm.
let's say the bigger it is, would it have like more capability to solve the tasks, or it's not how it works?
Well, I mean, nobody quite has solved what we call the vascularity problem. And so there are two ways you can scale this up. One is the biological scaling. So you make them three-dimensional, you do them as what we call organoids. So organoids are little spheres of these brain cells that are agglomerated. And we've grown them in the past as well. But the reason we don't really do too much organoid stuff is because A, it takes a long time to grow them. B, there's a ton of variability that gets involved when you grow organoids, right? So you can't make cells that are very, what's the word, consistent. And the other thing as well is that you're butting against physics. So the issue with any three-dimensional structure is that you've run into the issue of surface area to volume ratio, in the sense that the larger your three-dimensional structure is, the less surface area you actually have in relation to the volume. And why this is important is because what you need is a higher surface area for diffusion processes to occur. So take for instance, like say the brain, right? The brain has all these folds, right? And the folds are actually there to increase surface area, right? So having a completely smooth brain doesn't really work because it's just, nothing would dissolve inside. Another very another couple of organs where you see this are like the kidneys and the microtubules. So not the microtubules, in the nephrons, you end up with a lot of infolding, and you have a lot of extra surface area that gets packed into that volume. And the lungs with the alveoli have the same thing as well. And it's all to try to increase the amount of surface area or interface for diffusion processes to go in and out. And the problem with organoids, is that we don't have that. And so the larger the organoids we have, the more of the inside core, the core of the organoids are dead, because there's not enough diffusion going through to feed the neurons and also getting the waste out. And so, until somebody figures out how do you build a heart and how do you have the thing pumping the stuff through into it, we're going to be limited to how big our organoids can get.
Okay.
And also, yeah, that's, three-dimensionality is quite important, I think, particularly for more complex computation, right? So we know that most of the processing in the human brain happens in what we call complex cortical column structures. So these are multi-layered, three-dimensional structures. And so I think, we shouldn't lose ourselves to the, excitement and hype about this, and be realistic about where we are here, which is that we're very early in this phase. We've shown that it works. The question is, how far can we push this? What new technologies need to be developed in order to make these things grow larger? And what are the ethics around it? Do we really want a system that is just like us, conscious in the dish, right? I think all of these are questions that need to be asked. And fortunately for us, we're focused really on helping the academic research community understand this. And it's still quite a fair way away for us to really worry about it.
Well, yeah, that's actually super intriguing. And yeah, like certainly new technologies comes with their own challenges and own
Mhm.
limitations, but new horizons as well. Like when you overcome, there is a lot possible. I think for the time being, we are getting close to our time. Uh,
Yep.
I think let's, put it out there, listen to a comment, see a comments, and then maybe we can do a second part where we will where we can concentrate on maybe some more detailed topics and maybe invite somebody else to our conversation, uh,
Yep.
some other researchers or scientists to have like more in-depth, because I'm a finance guy actually, so uh,
Yep.
my interest is kind of, I would say, science, but also in finance part of it. But yeah, maybe that's in the future. Um,
Yep.
I really appreciate your time, and maybe you want to say a couple words before we end.
Um, well, I think, firstly, thanks for having me on the show, and it's really important that even finance people keep an eye out, right, on what's coming, right? Because you guys are all about the alphas, right? And unfortunately, if you don't push or create new things, the alpha you get is quite minimal. And at the end of the day, it's all about a question of what is the risk tolerance, and how much are you willing to trade for that. And I feel like this field is very risky because we don't know enough about this. We have no idea. Um, and it really does take a bit of a leap of faith for someone to do this. And really great, thanks to our investors for coming along and helping us along the way. But yeah, I think the finance and the venture capital community really need to start thinking about, where are we going next, right? I mean, we've poured trillions of dollars into quantum computing and AI. And I think now it's up to them to really like show whether they can actually live up to the expectations, but not to foreshadow a lot of other interesting avenues of research and development, right? That's the whole point of it, which is why concentrate your capital into one sector when you can spread it around and see which one works. The original VC model of the log return. So, I think it's really important people understand that people take risks, people understand, because your returns are going to be the same anyway. If you put into a scooter company, there were 10 of them and pretty much all of them are dead now. So that investment has gone to zero.
Yeah. We need more meaningful research stuff like that.
Correct.
Yep, that's a really good point. Okay, I'm really thankful for
Yep.
your time and for conversation. Thank you. We will end.
Okay. Thank you. Bye.